Hello everyone, my name is Martin and I'm an engineer in Intel, and for the last couple of years we've been working with Redis on tuning and enabling Redis for our latest technology, persistent memory. As Ken just mentioned in the keynote, it launched yesterday, and so we're very excited to share some performance data for the first time. In this presentation I'll go over what is persistent memory, what are the different modes in which it can be used. I will talk about what are the advantages and use cases for Redis that can take advantage of this new technology. And finally, I'll end up with a live demo of showcasing performance of DRAM side by side with persistent memory. Okay, so what is Intel Optane persistent memory? It's a new revolutionary technology that Intel actually just launched yesterday, officially launched yesterday. It has attributes of DRAM, such as low latency. The usual access latency to access DRAM is 70 to 80 nanoseconds. This is a couple hundred to several hundred nanoseconds. So it's in the same order of magnitude of latency as DRAM. So it's a very fast, low latency memory. But it's based on a completely new storage media. It's not DRAM, it's not NAND, it's what we call Optane media. It's a new storage media, and an inherent property of that media is actually persistence. So when you turn off the power supply to the system, this retains the data. So it has attributes of DRAM, which is low latency access. It has attributes of storage, which is high capacity and persistence, and also is going to scale well going forward. The capacity is going to scale better than DRAM going forward as well. So, as I said, we launched the persistent memory product yesterday in San Francisco as well with the new Cascade Lake Intel CPU. This is the CPU that will support the new memory technology. And with this CPU, we have support for the new persistent memory. The memory technology looks just like any DIMM. It's a DIMM form factor. You can mix and match DRAM DIMMs as well as persistent memory DIMMs on the same system. It will be electrically and physically compatible with DRAM. Looks just like a DRAM DIMM. Close to DRAM latency, as I mentioned. Cache line access granularity, think of it as memory. You access it just like any other memory. It will have larger capacity. So it will have 128, 256, and 512 gigabyte per DIMM capacity in the first generation. So what that means is that in a two-socket system, if you populate six 512 gigabyte DIMMs per socket, on a two-socket system, you will have 6 terabytes of data, of memory per system. And it will be cheaper too, $1 per gigabyte than DRAM. And there are two modes in which you can access this memory. The first mode is what we call memory mode. And in this mode of operation, what happens is the hardware will treat DRAM as a transparent cache to the persistent memory. Think of it as a level 4 cache. It's treating the DRAM as a write-back cache to persistent memory. So in this scenario, software will see 1 terabyte of memory capacity in the system. Even though you have 1 terabyte of persistent memory and 256 of DRAM, you're only going to see the 1 terabyte. The 256 is being used as a cache for the persistent memory to achieve close to DRAM latencies at larger capacities. So this is memory mode. And we also have what we call app direct mode. In this mode, software will see 2 memory pools. It will see your DRAM as before, and then you will see another pool of memory, which is the persistent memory. It will be exposed to you as a file system. You can memory map that file system, and from that point on, you have direct load store access to that memory media, just like memory, and you have more control in software deciding where to place your data in DRAM or in persistent memory, depending on the characteristics of your workload. And in app direct mode, you can also take advantage of the persistence. Now, whatever you put in persistent memory there in app direct mode will remain past the reboot. Versus in versus in memory mode, persistence is not enabled. And for this talk, last year we talked about, just one more thing I would like to mention. In AppDirect mode, there's actually another mode, sub-mode of AppDirect, which we call storage over AppDirect. In this case, you can use the persistent memory as a very, very fast disk. You treat it as a block device. And so for Redis, in this talk, I will focus mostly on memory mode, but it works in both cases. For memory mode, Redis Enterprise or Redis open source unmodified works because this is transparent to software. The caching of DRAM is handled completely in hardware. All the software sees is just more memory capacity. That's it. Last year on this stage, together with Oran, we actually presented our work that we did it with Redis Enterprise on enabling Redis on Flash for AppDirect mode. In this mode, instead of using Flash on Redis on Flash, we're able to use this new persistent memory and achieve higher performance. So this is Redis on Flash. For today, I'll talk about Redis Enterprise in memory mode, which was announced. Memory mode was just announced yesterday. So just a little bit more detail about memory mode. Again, no software application changes are required. It's completely transparent to software. So for all practical purposes, the operating system doesn't even know there's different memories installed in the server. It just sees more memory, and software can take advantage of it. Data by default is encrypted on the persistent DIMM, but for memory mode, because we're treating it as volatile, the encryption keys are discarded to make it look volatile. We call DRAM, in this mode, memory mode, we call DRAM near memory, and the persistent memory is far memory. And near memory is a cache to persistent memory. And you can have different ratios of near memory and far memory depending on your workload characteristics. Typically, we would see 1:4 or 1:8 ratio of near memory to far memory capacity. So let's say 256 gigabytes of DRAM to 1 terabyte of Apache or Optane DC persistent memory. I'll just call it persistent memory. In this slide, one more level of detail of the flow of accessing data from this memory. On a cache hit, you'll get your data from DRAM with DRAM-like latency. On a cache miss, the memory controller will go out to the persistent memory and fetch your data from the persistent memory. So again, it's completely handled in hardware in the memory controller of the CPU. As far as software is concerned, there's no changes. There's some performance implications here. Depending on your workload characteristics and the locality that your workload exhibits, you will have a different near memory versus far memory hit or miss rate, right? The more often you hit from DRAM, the better your performance will be because DRAM is still faster than this new technology. So your near memory hit rate will have an impact on your performance. In addition, read versus write now will have impact on your performance. Writes are slower to this media than reads. And so read-write ratio also has an effect on performance. And finally, bandwidth demands. There's less bandwidth capability in this memory than regular DRAM. Just a ballpark number, you can expect roughly 2 gigabytes per second per DIMM of read bandwidth from this memory, roughly, depending on different characteristics as well. So what are some of the benefits that you can see with this, with Redis Enterprise? Improved total cost of ownership. As I mentioned, this memory is cheaper, especially for large deployments. As Ishtaf mentioned, we're going to terabytes and petabytes of deployment. If you're using megabytes, that's not for you. If you're using large deployments, you will see benefit. Consistently great SLAs, you will see in my demo, we're able to do upwards of 1 million transactions per second at sub-millisecond latency for large data sets, and higher memory capacity. What are the typical use cases? Oops, this is auto switching. So we have collaborated with Redis Labs for about 2 years on both the app direct and the memory mode usage for Redis Enterprise. And today we're finally able to show some of our performance data. But the key customer pain point that we're solving is DRAM is expensive, and Redis is an in-memory database. And many customers face a problem when they start scaling to multi-terabytes and petabytes. DRAM becomes too costly to fit all their data in Redis. And so what they end up doing is they end up going to a multi-tiered solution where some of the data is Redis, the hot data is going to be in Redis, and the cold data is going to be on some other store. With this technology, we believe that now you can put all your data in Redis and keep it in sub-millisecond latency readily available. Okay, Ishtaf talked about this during the keynote. This is not this solution, we believe, will fit a majority of workloads where they need high capacity and high performance. On the y-axis here, you have capacity requirements for your deployment. On the x-axis is latency. And this part of the graph shows Redis on flash, where you need large capacity but low throughput requirements. DRAM is on the bottom. And persistent memory can serve, we believe, the needs of majority of customers who need greater than 1 million ops per second at sub-millisecond latency. And on that slide also I showed during the keynote, for the same capacity system, now that you know about the different modes of operation, this is in memory mode. In memory mode, both of these systems will show 1.5 terabytes of capacity. The DRAM here, 192 gigabytes of DRAM, is used as a hardware-managed cache. It's not visible to software. Same capacity, same throughput, or for the demand, the common customer SLA demands more than 1 million ops per second. Both systems can meet that at a significantly lower cost of memory. And that includes the cost of DRAM as well. So you're paying for both, and you're still going to get a 43% benefit. Another common usage which we want to highlight here is once you start scaling to a large data set. Let's say you have a 20 terabyte data set. You need to service more than 2 million ops per second and a millisecond latency. Then what do? Today, one of the most cost-effective ways you can do that in DRAM is you fully populate the DRAM system with 64 gigabyte DRAM modules for 1.5 terabytes, and you need 17 servers. With this new technology, you need half the number of servers if you populate them to 3 terabytes, and you're going to also save on OpEx expenses, fewer racks, switches, etc., for large deployments. With that, let's go to a demo. Okay. So for this demo, I have 3 systems. This system here on the bottom is my persistent memory system. It's configured with 1.5 terabytes of persistent memory. If you look at the memory capacity is 1.5 terabytes in memory mode. The system on the left is my DRAM system. It has 1.5 terabytes of memory. They have the same CPU. Everything else is identically configured. However, if you look at under the hood a little bit more, in DMID code, you will see the memory devices populated in the system. We have some 16 gigabyte DRAM DIMMs, 16 gigabytes here. And these DRAM DIMMs are intermixed with some persistent memory DIMMs, which are 128 gigabytes per DIMM, right? So the system is intermixed with DRAM and persistent memory DIMMs, but the total capacity is just the capacity of the persistent memory exposed to software. Okay, and the third system is actually a client system which we're going to use to drive the workload over the network. Both systems are configured with two 40 gigabit adapters bonded, so they have 80 gigabit network connection to the switch to make sure network bandwidth is not an issue. And the third system is going to be a client serving workload. Now, on the demo slide, this is the graphical user interface of Redis Enterprise that we all know. On the left, this first system, I have two tabs connected to the two different systems. This one is the persistent memory system. I have 6 billion keys of 100 bytes each. So that adds up to be about 1 terabyte of data is populated in the system. I have 1.04 terabytes of data. Now the 1 terabyte data set is greater than the near memory DRAM cache, right? You want to make sure that we're fully utilizing all the capacity and exceeding the near memory cache. And the other system is configured in the same way. 6 billion keys, 100 byte values, DRAM only. So let's see how they perform. So this is the client system from which we're going to serve the workload. We're using the memtier benchmark, which hopefully most of you know is what we benchmark Redis with. We have specified 6 billion keys, 100 byte values. Pipeline, so we specify 18 concurrent client threads, clients, 18 threads per client, 18 pipeline requests. So we're just spawning a whole bunch of concurrent client requests. We're specifying randomized, so all the clients will serve random key value requests. We're not using any Gaussian pattern distribution. This is purely random access across the entire space of entire key value space. And the read-write ratio is 50-50, so 50% reads, 50% updates to the keys. So when we start this up, in the GUI, you will see that we are achieving about 2.3 million ops per second at a sub-millisecond latency in DRAM. So what I'll do is I'll stop this test and I'll reuse the same client server to drive work to the persistent memory system. Again, remember we saw about 2.4 on average million ops per second under 1 millisecond SLA from the DRAM system. Here on the persistent memory system, we're launching the same exact test. Same parameters, same number of concurrent threads and everything. And you will see, once we switch over to this system, you will see that I launched the test differently. 18, we need to push it more. So you will see that we're going to also reach upwards of 2 million ops per second at a sub-millisecond SLA. So we're able to see very, very high throughput, very close to DRAM performance. In fact, if you average it out over a number of runs and for a good duration of time, I've seen in my testing an average of 18% throughput difference between DRAM and persistent memory for this test. But that's at the peak performance. So when you're pushing at the peak throughput under 1 millisecond, as close as possible to 1 millisecond, we're getting about 18% delta. But for anything less, if you're doing here, if I quickly show, for example, a little bit less highly loaded system, then performance between DRAM and persistent memory will be the same. So if I launch fewer threads and we're achieving 1.5 million ops per second, latency is much below 1 millisecond, and performance will be very close to DRAM, or the same as DRAM. And this is the demo, and I can show on the hardware side. So here, we can do, for example, let's see if this tool is going to render. So we have a tool, I hope it's visible. We have a tool to, in real time, show you the bandwidth that is currently being demanded from the DRAM as well as from the persistent memory DIMMs. And you can see, if you look at memory read megabytes per second, memory write megabytes per second, this is per socket. So each socket is doing about, currently each socket is doing about 880 megabytes per second of DRAM bandwidth, and very little. The test must have ended. Let me see. Let me run it for a little longer. We can see we're doing about 3 gigabytes reads and writes per second per socket from the DRAM near memory cache, and we're doing about 400 megabytes per second read per socket from the persistent memory. So even though we're doing completely random access pattern across the 6 billion keys, we're still able to capture majority of the traffic from the near memory or from DRAM cache. And I think with that, I'll open up for questions. I can show some other metrics, but I would like to have time for questions as well. Yeah.
Okay, so this demo that you just showed is the memory mode configuration.
That's correct.
Correct. Okay. Earlier you said that for the memory mode, the persistence is not enabled. So can you clarify on that? Like, so what happens if I reboot the server?
Then it's just like DRAM. Then
so data's gone.
Data's gone.
Data's gone. Okay.
Data's gone. Persistence is there, but the memory is encrypted. So when you reboot the system, the encryption key is discarded, so you cannot make sense of the data.
So the actual data is not stored, like it's not on disk. It's not any.
No.
Okay.
It's not persisted.
I see. Okay, thank you.
Yeah.
Okay, any more questions? Please raise your hand if you have a question. Oh, here we have one.
First of all, thanks for the interesting talk. Can you use, how would you use the persistent mode with Redis, please?
Yes, we actually talked about this last year in the same conference. We use it in Redis, or Redis on Flash. So in Redis on Flash, your hot data is kept in DRAM, and your cold data or cool data is kept on Flash. And the part that manages the flash is a storage engine such as RocksDB or LMDB manages the flash. So anytime you want to get something from flash, you talk to that storage engine. What we did in our collaboration with Redis is instead of using flash or SSD, we used the persistent memory for that. So the storage engine was enabled to talk to the persistent memory. And so then you get the benefit of extended capacity, because now you see both the capacity of the persistent memory as well as the DRAM capacity. So you see both memory pools, so you have an extended capacity. Does that?
Let me ask another question. If I would like to use the persistent memory, but in persistent mode with Redis, how can I do that?
So for the persistent mode, you need the app direct mode. The memory mode is not persistent. Yes. Memory mode is completely transparent, makes it easy for software that does not need to make any software changes. But in order to take advantage of the persistence, you actually will need to modify your software to take advantage of it. For example, if you want to take advantage of the persistence, you need to think about considerations such as you need to flush your data to the persistent media to ensure that it has reached persistent media. Sometimes your data may be in the level 1 caches of the CPU or level 2 or in anywhere else in the memory hierarchy. And you need to, if you want to ensure persistence, you need to make sure it's flushed to the persistent memory and it reaches persistent memory. So if you want to take advantage of persistence, that will require some software changes. In Redis on Flash, what we did last year, we used app direct mode, but we did not take advantage of the persistence. We just took advantage of the capacity, just like Redis on Flash. Redis on Flash uses SSDs to make it look like you have more memory, but persistence is handled orthogonally using another approach.
Thanks.
What's the minimum configuration? Is it 1 terabyte?
No, the minimum, the smallest DIM is 128 gigabytes. So in reality, you can just put one DIM, and you're going to see 128 gigabyte memory pool. In app direct mode, you can configure that as a 128 gigabyte SSD. It's not an SSD. It's like using a Ferrari for your lawnmower, but you can do that.
Okay, any more questions? Yeah.
Hi, I have two questions. The first one is when you're running Redis in memory mode with the in-memory persistence, could you run a benchmark in such a way that all the reads always go to the persistent memory, and your DRAM is somehow kept busy by some other mechanism, but all the reads always go to the persistent memory?
No, it cannot. Hardware will treat DRAM as a last level cache. So anytime hardware accesses data in memory mode, it will first look in DRAM.
Okay.
If it's not in DRAM, it's going to go to the persistent memory and it's going to bring it into DRAM.
Okay.
And then it's going to replace whatever was in DRAM cache out to persist. So it's just like a cache, hardware managed cache.
Okay.
In app direct mode, you can do what you just said. In app direct mode, you can talk directly and only to the persistent memory.
Okay.
Yeah.
I missed a couple of sessions at the beginning, a couple of slides in the beginning. Do we have any roadmap for AD mode for Redis?
So app direct mode already works with Redis on Flash.
I see, okay.
Because Redis on Flash can extend memory capacity onto SSDs, now you can extend memory capacity into this persistent memory as well.
Okay.
But it doesn't take advantage of the persistence yet. This is a kind of future conversation. It takes advantage of the capacity.
I see. Okay, got it. Thanks.
Yeah. No more? Okay. Any other question?
Yeah, that was a question there.
So thank you for the presentation.
Sure.
I think you mentioned something about encryption. Could you expand on this? You said that you encrypt with keys and then you can just throw away the key.
Yes, yes. So by default, the DIM, the persistent memory DIM is encrypted. And it's a hardware managed encryption. There's a controller on the DIM which does the encryption and decryption. There's no performance implication for that. Now, for security reasons, because if you treat the memory in memory mode, the expectation is that it's volatile. The expectation is you don't even know it's different memory. It's just software doesn't even care. And if the expectation is volatile, we ensure that it's volatile by discarding the encryption key from the controller on the DIM every time you reboot. So each DIM on the controller has a unique key. And if you move that DIM to a different machine, now you need to, when the machine boots up, you need to supply the path phrase to decrypt the DIM, and then you can use it. In memory mode, it's just encryption is discarded.
I apologize if I missed this on the slides, but I was wondering, do you have exact numbers on how long it takes to do read and writes to the persistent memory portion? Or
Sure. I have more detailed numbers. So the numbers are not straightforward. I cannot just say 80 nanoseconds because, again, it depends on the read versus write, and the other considerations. But I have some slide in the backup that gives more detail there. So this slide shows your range for read latency will range from 180 to 340 nanoseconds for an idle read, depending on the load of the system, the curve, will change, and also depending on the read-write mix, the curve will change. So you will see here we have latency on the y-axis and you have bandwidth on the x-axis. As the bandwidth increases, there will be impact to your latency as well. So, but roughly, again, roughly for reads, this is your latency for reads as compared to DRAM, which is 70 nanoseconds. For writes, it can go higher than that, too. Because again, the media is persistent. You need to think about the memory controller on that DIMM needs to do wear leveling and all sorts of stuff treated as any other persistent media. There's some more work to be done for writes.
Thank you very much.
Yeah.
Okay, any more questions?
Yeah, there's a question.
Okay, yep.
What OSs are these servers available to be purchased with?
So in memory mode, as I mentioned, software doesn't even know about it. It's purely handled in hardware. So if you boot up a system with an OS in memory mode, it should work. As far as app direct mode, all the major OS vendors are working on supporting this. There's some, I don't know which ones have announced what support. So SUSE has officially announced support for app direct mode. Yeah, so the major vendors, just to repeat, the major vendors have all announced support for this, and it's just a matter of timing after the launch. Yeah.
Any more questions? I think we're done then. Thank you very much, Martin.